Okay, we're looking at inscribed angles, and let's go ahead and start by defining them, although we already did back in, I believe, 11.1. Inscribed angle is basically an angle formed by two chords whose vertex is on the circle. Is on the circle. So for example, angle ABC, do I have two chords? And is the vertex on the circle? For sure. And then I want you to draw a central angle, A to the center to C. And we know whatever the central angle is, the arc will also be congruent to. Here we have. Oop. So let's pretend that, I know it's not drawn to scale, let's say we have 60 degrees. What else is also 60 degrees? The arc is also 60. And then the inscribed angle, let's kind of analyze. The angle made by the central angle, is it obvious that that one is bigger than the inscribed angle?
Yeah.
The rule is, it is always the half. Inscribed angle is always the half, or the arc is double the inscribed angle, whichever way you want to look at it from. And let's do a quick reminder that I had you guys start on the last notes. Central angle is always congruent to the what? The arc. So let's do our example number 1. Let's start by connecting our central angle. And I'm going to put on here x, y, z is 55. And just to be consistent, why not highlight it with the same one that we did previously? I think I want to go ahead and highlight the arc too. To find the arc, am I going to half it or double it from the existing number? Double. And then just for practice sake, let's also put central angle is 110. Okay, let's try example A and B with the partner. Go. Talk to your neighbor. I know it's Friday. Still talk to your neighbor. Okay, Charlie, what'd you get for angle cat? 65. Because the arc and the inscribed is, well, inscribed is half of the arc. So we took 130 and divided by 2. Okay, Nathan, what about B?
I didn't do it.
You didn't do it. Let's do it together. So we know angle DOG is 15. This right here is 15. So Nathan, to find the arc, do I double the 15 or half it? Double it, very good. I want to keep the picture on the next one, but I don't care about this right here. It gets quite confusing. So here's what I want you to do. Take your one highlighter, go ahead and highlight one of the inscribed angle, just one of them, and then the intercepted arc. And take a third color if you have. Highlight the second inscribed angle. What is the commonality between these two inscribed angles? The arcs are the same. So we have a common arc. So because it's sharing the same arc, what can I say about the angle measurements of those inscribed angles? They're the same. So let's put on here, therefore, the 3 dots represent therefore, angle XYZ is congruent to angle XAZ. So much more simple than going through the question errors, okay? So then on the back, let's go to number 3. Okay, on number 3, it's asking us to kind of go through each part. Let's actually do that. And I want to go ahead and highlight the inscribed angle with the same color. or whatever color you want. And then the arc. The intercepted arc. Now, just by looking at this, is AC a chord or is it a diameter? Diameter. Can I also call it a chord? Yes. But which is even better answer? Diameter. So we know AC is a diameter. So therefore, angle ABC has to be what kind of angle? It is called the inscribed angle, right? Is it a right angle?
Probably.
Okay. I think you're right.
I think so. I don't think I'm right.
We know this arc, half a circle is going to be 180, right?
Yeah.
Uh-huh. So what is the intercepted arc? In this case, we have a semicircle. And because when I use 2 points, it's typically understood as a minor arc. Let's go ahead and add extra letter. So I'm going to go ahead and call this one the measure of the arc. ADC, and put a swing around it, has to be 180. And someone did already say that the inscribed angle was 90, right? Very good. So we know measure of the angle ABC is 90. So here's the idea where you might be like, I don't buy into it, but we're going to have to. This means as long as I use my A and C as my endpoint, no matter where I make my angle, it's always going to be 90 degrees because it's hitting the endpoints of our diameter. Okay? If you really get bored tonight, draw yourself a big circle, move the vertex around, and then get like the corner of your paper, it'll always hit it. Unless it's figure not drawn to scale, right? All right. So let's go on to the next piece on the bottom. Okay, there's a theorem that you should know. Put a star on this one. Maddie, let's read the theorem.
A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplemented.
So opposite angles are supplement. Would you agree angle 1 and angle 2 are opposite of each other? So that's going to be 180. Furthermore, I'm going to call this angle 3 and angle 4. So when I also add angle 3 plus the measure of angle 4, that should also be how many? 180. As long as your opposite angles are 180, no matter what, you can fit a perfect circle around the vertices at all times, which is kind of interesting. So let's look at the first one on the bottom. Can a circle go around the figure, meaning the theorem right above? So let's compare. I got 85 and 95. Is that 180 together? Yeah? And then I have 110 and 70. Is that 180 together?
Yeah.
So we know a circle will go around the vertex and make it a perfect circle and not an oval. Second one is quite annoying because there's no number on it. Let's make up a number. If I tell you this is 50, where else can I write the 50? To bottom right? Okay? And then we're going back to like unit 3 or 4. If 2 lines are parallel, cut by a transversal. These two are what to each other? Supplement has to be 130. And since we have an isosceles trapezoid, the other two has to be identical, so 130 as well. So just by looking at that, can a circle go around it?
Yeah.
Yep. And then our last one, can the circle go around it? Because when I have 110 and 110, or 70 and 70, that's not going to make it 180. Okay, our last part. Given circle O, I'm going to model the first one with a B. It says to name the intercepted arc of MPL. So let's go ahead and highlight MPL. You kind of have 2 options ideally on this one. Is this arc a major or minor? If it is minor, how many letters can I use to name the arc? 2. So I could go ahead and say ML. Or you might go, well, can I go ahead and collect the letter in between? For sure. You could say M and L, as long as in the end it is going around the same arc. Okay? So let's go ahead and name the rest of them with the partner. Last piece. Okay, someone give me the intercepted arc of MNP. Arc what? MP. Could I say PM? Yeah. As long as you completely reverse it, it's fine. Now it's saying, is PMN a semicircle? Yes or no?
Yes.
And how do you think I want you to define that? Why?
The inscribed angle is
Point on the diameter. So we have PN is a diameter. And that is exactly what I wanted.
Could you say it's because angle N is 90 degrees?
Yes. But then you would have to say the inscribed angle M is 90 degrees. So therefore, blah, blah, blah. But I would take that as well. And then what about PK? Is PK major or minor? Minor. Arc. Now, it's saying what is. So my assumption is it's probably asking for the measurement, right? So if I want the measure of PK. PK is right here. And we have the intercepted arc of 30. Do I double or half it?
Double.
Double, which is 60. Very good. What is the name of the angle MPN? We have MPN.
semicircle.
What is the name of it? What kind of angle?
A cube?
It is an inscribed angle. And yes, it is a cube. Acute. Inscribed angle. And specifically, what kind of acute? Tucker? How many degrees? Because you're right.
45
Boom. How'd you get 45?
from, I think, yeah, 45, 90.
There you go, 45, 45, 90. We have an isosceles right triangle. Good job. What about MN? Is it a minor or a major? Another minor. Arc. And specifically, the measure of MN is how many?
90.
90. And we know that how? You multiply by 45, or if you make the two radii, it's going to create the 90 degrees. But we have 45. Ooh, y'all said 90, right?
Yeah.
Silly me. So here's 45. Double that must be 90. Okay?